3 minutes ago, astronomers announced the confirmation of something so extraordinary that it validates a prediction made nearly 50 years ago by a woman who never lived to see it proven. They found a galaxy with almost no dark matter inside it. And not just one, 3 of them lined up in a perfectly straight line across the cosmos. But here is what makes this story genuinely remarkable. Vera Rubin predicted this would happen. She didn't predict it explicitly or by name. She didn't know about galaxies like DF9 or the bullet dwarf collision theory, or even the ultra-diffuse galaxy category that wouldn't be formally recognized until after her death. What Vera Rubin predicted was something far more fundamental. She predicted that dark matter was real, and if dark matter was real, then it had to be possible, under the right extreme circumstances, for ordinary matter to separate from it, for galaxies to exist without it, for the invisible hand holding the universe together to occasionally let go. And now we have found those exact circumstances playing out in the cosmos, exactly as the physics her discovery enabled would predict. Vera Rubin's career is one of the most compelling stories in the history of science, and it is also one of its great injustices. She was born in 1928 in Philadelphia to a family that nurtured her astronomical interests from childhood. She grew up watching the stars, asking questions that conventional astronomy of the era could not answer, and pursuing a path that very few women were taking in mid-20th century science. By the time she earned her PhD in astronomy from Cornell University, she was already publishing original research. But the real breakthrough came in the 1970s, when she began a systematic study of how galaxies rotate. This might sound like a straightforward observational task. You point a telescope at a galaxy, measure how fast stars at different distances from the galaxy's center are moving, plot those velocities on a graph, and you have a rotation curve. That is exactly what Rubin did. Except when she looked at the data, it told her something that contradicted almost everything astronomers believed about how galaxies work. According to gravitational theory, stars at the outer edges of a galaxy should orbit more slowly than stars near the center. This is basic orbital mechanics. The outer planets in our own solar system orbit the sun more slowly than the inner planets. Mercury travels around the sun at roughly 47 kilometers per second. Neptune, billions of kilometers farther out, orbits at only 5 kilometers per second. This is not complicated. The farther you are from the gravitational source, the weaker the pull, the slower you move. Galaxies should work the same way. Stars at the center should orbit quickly, stars at the edge should orbit slowly, and a rotation curve should show velocity declining as you move outward from the galaxy's center. This prediction comes directly from the visible matter in the galaxy. Add up all the stars, all the gas, all the dust you can actually see with a telescope, calculate the gravity they produce, and calculate the orbital speeds those speeds should create. The math is straightforward. The problem is that when Rubin measured actual galaxies, the rotation curves did not match the prediction at all. Instead, the stars at the outer edges of galaxy after galaxy were moving far too fast. They were moving nearly as fast as the stars at the center. The rotation curve stayed flat instead of declining. This should not be possible. According to the visible matter calculation, those outer stars should have been moving so slowly that they would have escaped the galaxy's gravity long ago. They should have flown off into space. But they had not. They were still there, still orbiting, still moving with velocities that could only be explained by one thing. There was far more mass in those galaxies than the visible matter accounted for. A vast amount of mass that gave off no light, that could not be seen by any telescope, that had no radiation signature detectable across the entire electromagnetic spectrum. There had to be something invisible, something massive, something everywhere that astronomers had been unable to detect. Vera Rubin did not invent dark matter. Theorists had proposed the concept decades earlier based on different observations. But Rubin's work provided the most direct, the most systematic, and the most compelling observational evidence that dark matter was not a theoretical curiosity. It was real, it was abundant, it was everywhere, and it dominated the mass budget of galaxies across the universe. The implications were staggering. If dark matter made up the majority of the mass in galaxies, then what astronomers thought they understood about how galaxies formed, how they evolved, how they held together, how they moved through the cosmos, all of it required revision. Rubin's careful measurements, replicated across hundreds of galaxies, showed that dark matter was not some exotic rare component. It was perhaps the dominant form of matter in the universe, more massive than all the visible stars, all the planets, all the gas clouds, all the atoms of ordinary matter that had ever been studied. And yet, nobody knew what it was. No particle physics experiment had ever detected a dark matter particle directly. No detector had ever captured the identity of the substance that makes up roughly 85% of all matter in the observable universe. What we had was gravitational evidence. We could measure its effects, we could map its distribution, we could see its fingerprints in the rotation curves of galaxies and the motion of galaxy clusters, but dark matter itself remained hidden. invisible not just to optical telescopes, but to every detection method science had yet devised. This was Vera Rubin's great discovery and her great frustration. She had proven that dark matter existed. She had provided the most compelling evidence in the field, and yet the Nobel Prize that might have recognized this achievement never came. She would spend the rest of her career studying dark matter's gravitational effects without ever knowing what it actually was. She died in 2016, never receiving the recognition many felt she deserved, and never seeing the specific implications of her work play out in ways that would become clear only after her death. The observatory that now bears her name exists partly as a recognition of what she started, partly as a continuation of the work she pioneered, and partly to answer the questions she left unanswered. Now, nearly 50 years after Rubin's foundational measurements, scientists have confirmed something that her discovery made theoretically possible. They have found galaxies that lack dark matter, not galaxies with less dark matter than expected, not galaxies where the dark matter is distributed unusually, galaxies that appear to have essentially no dark matter at all. The first of these galaxies, called DF2, was discovered by Yale astronomer Peter Van Dokkum and his team in 2018. DF2 sits in a region of sky near a larger galaxy called NGC 1052, about 65 million light-years from Earth. When Van Dokkum measured its velocity dispersion, essentially the spread in speeds of stars moving within the galaxy, he found something shocking. The stars were moving slowly, far more slowly than they should be if dark matter were present in normal amounts. If DF2 had a typical dark matter halo for a galaxy of its size, the stars should have been moving at roughly 30 kilometers per second. Instead, they were moving at only 8.5 kilometers per second. This was not a small difference. This was a factor of 3.5 slower than expected. The measurement suggested that DF2 contained 400 times less dark matter than theory predicted. The announcement generated immediate scientific controversy. Several research groups published papers questioning whether the measurement was correct, whether the distance to DF2 had been accurately determined, whether observational uncertainties might account for the result. After all, you cannot see dark matter directly. You can only infer its presence from gravity. What if something was wrong with the inference? What if the team had made an error in calculating DF2's distance, which would throw off all the subsequent calculations? What if some other factor was being overlooked? The debate continued for years, but Van Dokkum and his colleagues responded with additional observations, refined analyses, and careful reconsideration of every potential source of error. They became progressively more confident in their original finding. DF2 really did appear to contain very little dark matter. Then came DF4, another galaxy in the same region of sky, also discovered by Van Dokkum's team, also showing evidence of extremely low dark matter content. Finding one galaxy without dark matter could potentially be explained as a statistical anomaly, an unusual object that happened to form under rare circumstances. Finding two in the same small region of sky was harder to dismiss as coincidence, but even with two confirmed examples, the underlying mechanism was still debated. How could a galaxy form without dark matter? Under what circumstances could ordinary matter separate from dark matter? These were the questions that made the third discovery so important. DF9 is an ultra-diffuse galaxy, which means it is spread out over a relatively large area of the sky, but contains far fewer stars than a normal galaxy of that size. It was originally misidentified by automated surveys as a supermassive black hole rather than a galaxy at all. It took a doctoral student named Michael Keem at Yale University to recognize what it actually was. Keem was working under Van Dokkum's supervision, continuing the investigation that had already uncovered DF2 and DF4. In 2022, Van Dokkum's team published a remarkable observation. They had identified roughly 10 low-luminosity galaxies arranged in a narrow linear formation stretching across the NGC 1052 field. These galaxies were not randomly scattered. They were not haphazardly arranged. They were aligned in a straight line, a configuration so statistically unlikely to occur by pure chance that it strongly suggested all of these galaxies had shared a common origin. They had formed together from the same violent event, rather than being separate, unrelated objects that happened to cluster together. DF2 and DF4 both sat along this linear trail. And based on the hypothesis that galaxies sharing the same violent formation event should share similar properties, including the absence of dark matter, DF9 became a compelling target for follow-up observation. The predictions were clear. If DF9 had formed in the same event that produced DF2 and DF4, then it should also lack dark matter. It should show the same signs of extremely low velocity dispersion. It should sit along the predicted trail at a position consistent with a collision origin model. The team proposed observing DF9 with the Keck Cosmic Web Imager at the W.M. Keck Observatory on Mauna Kea in Hawaii. This instrument is specifically engineered to study faint, diffuse sources of light, exactly the kind of light emitted by an ultra-diffuse galaxy like DF9. The observations began in October 2024. The team gathered data for more than 10 hours across 2 separate observing nights, accumulating enough light from DF9's extremely faint stellar population to measure something called the line width of the galaxy's stellar absorption features. This measurement directly encodes how fast the stars inside DF9 are moving relative to each other. What they measured was striking. The velocity dispersion of DF9 came out to 6.5 kilometers per second. To understand how extraordinary this is, you have to understand what the expectation was. If DF9 had a normal dark matter halo for a galaxy of its size and stellar mass, the expected velocity dispersion would be approximately 24 kilometers per second. The measured value of 6.5 is roughly a quarter of that expected figure. This is not a marginal difference that could be explained by measurement uncertainty. This is a factor of nearly 4 below the prediction. The confidence in this measurement is extraordinarily high because of how much observation time was invested in accumulating enough signal from DF9's faint stellar population to measure the velocity dispersion with statistical certainty that rules out a normal dark matter halo. The total measured mass of DF9 came out to approximately 100 million solar masses. That is a solar mass being the mass of our sun. 100 million times the sun's mass sounds enormous, and in absolute terms it is, but for a galaxy of DF9's size, it is tiny. If dark matter were present in the normal amount, a galaxy of DF9's dimensions would be expected to contain more than 10 billion solar masses. The absence of that dark matter is not subtle. It is not marginal. It is dramatic. The visible matter, the stars, the gas, the dust, accounts for essentially all of DF9's mass. Nothing else is there. The dark matter is simply not present. But here is what makes this third discovery so scientifically powerful. DF9 was not discovered randomly. Scientists did not happen upon it by accident and then measure it. The team made a specific prediction about where to look and what they would find if their theory was correct. The collision origin model predicted that DF9, sitting along this linear trail in a position consistent with a collision event, should lack dark matter and should produce a low velocity dispersion measurement. The measurement confirmed the prediction precisely. That is not luck. That is not coincidence. That is the gold standard of scientific evidence. A hypothesis makes a prediction. Independent observation measures what the hypothesis predicted. The measurement agrees with the prediction. This is exactly the kind of evidence that separates a solid pattern from coincidence and elevates a hypothesis toward established scientific understanding. This is where the mechanism of galaxy formation without dark matter becomes crucial to understanding. How does a galaxy end up without dark matter? The leading explanation is called the bullet dwarf collision theory, and it is one of the most visually dramatic concepts in modern astrophysics. The idea is that at some point in the past, 2 galaxies collided at extremely high velocities. When galaxies smash together at these speeds, something remarkable happens. Dark matter and ordinary matter behave completely differently. Dark matter interacts with almost nothing. It does not interact with other dark matter. It does not interact with ordinary matter in any electromagnetic way. Dark matter passes through ordinary matter like a ghost, completely unaffected by collisions, heat, radiation, or any of the interactions that slow down ordinary matter. So in a high-speed galactic collision, while the gas and stars from both galaxies slow down, heat up, interact with each other, and clump together in the collision zone, the dark matter from both galaxies keeps going. It is not deflected. It is not slowed down. It passes straight through the collision event, separating from the ordinary matter in the process. In the aftermath of such a collision, clumps of ordinary matter left behind in the collision zone can cool, condense, and form new small galaxies. Galaxies made entirely of ordinary matter with essentially no dark matter remaining because the dark matter kept moving and left the scene. This exact phenomenon has been observed on a much larger scale in an object called the Bullet Cluster, a pair of galaxy clusters that collided roughly 150 million years ago. Astronomers mapped this separation using gravitational lensing, the same technique that bends light around massive objects to map dark matter's distribution. The Bullet Cluster provided one of the most direct-eyed and compelling pieces of evidence that dark matter is real and behaves completely differently from ordinary matter. The formation of DF2, DF4, and DF9 appears to be a smaller-scale version of this exact same phenomenon. A dwarf-scale collision event where ordinary matter got separated from dark matter, leaving behind a dwarf galaxy made of ordinary matter alone. This is where Vera Rubin's prediction becomes directly relevant. Rubin did not predict DF9 by name. She did not predict the specific mechanism of bullet dwarf collisions. She did not predict the existence of ultra-diffuse galaxies or linear alignments of galaxy trails. What Rubin predicted, through her measurements of dark matter's gravitational effects, was that dark matter was a real physical component of the universe, distinct from ordinary matter, with its own properties and behavior. And if dark matter was real and distinct, then under the right extreme circumstances, it had to be possible for it to separate from ordinary matter, for the two components to be physically divided during violent events, for galaxies to exist that had been stripped of their dark matter halos. Rubin's discovery of dark matter's reality made all of this theoretically possible. And now we have found it happening exactly as the physics enabled by her work predicted. The discovery of DF9 also provides crucial challenges to alternative theories that some physicists had proposed to explain the earlier DF2 and DF4 observations without invoking dark matter at all. The most prominent of these alternative frameworks is called modified Newtonian dynamics, or MOND. MOND proposes that instead of dark matter being real, the law of gravity itself works differently at very low accelerations in a way that can mimic the effects we attribute to dark matter. If MOND were correct, then in principle there should be no galaxies without dark matter, because the modified gravity would always produce the same effects regardless of where you looked. But finding three galaxies that genuinely lack the effects that MOND was designed to explain, lined up in a trail consistent with a violent collision origin, is a significant challenge for MOND-type theories. It is not necessarily a disproof in absolute isolation, but it is an increasingly difficult anomaly for those frameworks to accommodate, especially as the evidence for a shared violent origin of all three galaxies grows stronger. The precision of the DF9 measurement deserves particular emphasis because it elevates this finding beyond previous discoveries. The Keck Cosmic Web Imager's ability to measure such an extraordinarily faint galaxy with the accuracy needed to definitively demonstrate its lack of dark matter is a technological achievement in itself. The team invested more than 10 hours of precious telescope time to accumulate enough photons from DF9's dim stellar population to measure its velocity dispersion with the statistical confidence necessary to rule out a normal dark matter halo. This was not a quick observation. This was not an incidental measurement. This was a carefully planned, precisely executed follow-up study designed to test a specific prediction. And the prediction was confirmed with a factor of 4 separation between measured and expected values. This is not ambiguous. This is not marginal. This is a clear, definitive confirmation. Michael Keem, the doctoral student who led the study, described the finding directly. He said the discovery provides some of the strongest evidence yet that these galaxies form through an extreme and previously unseen process that offers a rare new window into the nature of dark matter itself. Peter van Dokkum, Keem's doctoral advisor, had previously led the Hubble Space Telescope observations that confirmed DF2 and DF4 as dark matter-deficient galaxies. The new DF9 result builds directly on that foundation, extending the pattern from 2 confirmed examples to 3, all aligned in a trail, all showing the same signature of dark matter absence, all supporting the same collision-based formation mechanism. But here's what makes this story truly remarkable in the context of Vera Rubin's legacy. The Vera Rubin Observatory, whose 10-year legacy survey of space and time began on June 30th, 2026, is expected to be one of the most powerful tools ever built for discovering and cataloging ultra-diffuse galaxies across the universe. Because these galaxies are faint, spread out, and contain very few stars per unit of area, finding them in large numbers has always required extremely deep, extremely wide-field imaging. Exactly the kind of imaging that Rubin's 3.2 gigapixel camera and 8.4 meter mirror is uniquely optimized to provide. As Rubin accumulates data over its 10-year mission, scientists expect it to reveal hundreds or thousands of new ultra-diffuse galaxy candidates in regions of sky near known galaxy groups and clusters, massively expanding the sample of objects available for targeted follow-up studies of the kind that confirm DF9's dark matter deficiency. Some of those new ultra-diffuse galaxies identified first by Rubin and then studied in detail with instruments like the Keck Cosmic Web Imager, may turn out to be additional members of other dark matter-free trails we have not yet discovered. Each one adds a new data point to our understanding of exactly how and when ordinary matter can separate from dark matter during violent galactic collisions. The team is planning to measure the kinematics of a 4th and possibly 5th galaxy along the DF2, DF4, DF9 trail. The farther those galaxies sit from the collision point, the fainter they become, making the measurements progressively more difficult. But if even one more galaxy in this line turns out to be dark matter deficient, it would add an almost irrefutable additional piece of evidence to the case. The connection to Vera Rubin herself gives this entire story a deeply meaningful resonance that goes beyond the scientific achievement alone. She spent her career measuring the gravitational influence of dark matter without ever being able to see it directly. She found its fingerprints in the rotation curves of galaxies, proved beyond reasonable doubt that it was there, and never received the Nobel Prize she arguably deserved for that work before her death in 2016. The observatory now carrying her name is being used to find the rare galaxies where dark matter appears to be almost entirely absent. And those galaxies, paradoxically, may teach us more about what dark matter actually is than almost any observation pointing directly at its presence. Absence, it turns out, can be just as informative as presence when the physics of why something is absent is well enough understood to be predicted in advance and then confirmed by precise measurement. This is what separates genuine scientific progress from lucky observations. Vera Rubin's work established that dark matter was real. Decades of subsequent work established how dark matter behaves in normal circumstances. Theoretical physicists developed models explaining how dark matter and ordinary matter could separate under extreme conditions. Astronomers predicted where to look for evidence of that separation. And then they went and looked and found exactly what the theory predicted. This is science at its best. Prediction, observation, confirmation, and the gradual building of understanding through repeated cycles of hypothesis and test. DF9 is a testament to Vera Rubin's legacy and to the power of systematic scientific investigation. It proves that her foundational insight about dark matter's reality was correct. It demonstrates that the universe is even stranger and more intricate than the minimum interpretation of her measurements required. And it sets the stage for the next phase of discovery as the Vera Rubin Observatory begins. Its systematic search for more ultra-diffuse galaxies across the full southern sky over the coming decade. The next major discovery could come from Keck measuring a fourth galaxy along this trail and finding no dark matter there either. Or it could come from Rubin flagging an entirely new trail of ultra-diffused galaxies somewhere else in the sky that nobody has cataloged before. Either way, it will build on the foundation that DF9 just laid. Vera Rubin never lived to see the Vera Rubin Observatory begin operations. She never knew that the observatory would bear her name. She never knew that a galaxy with almost no dark matter would be discovered, and would confirm in such precise detail the implications of her foundational work. But her legacy lives on in the questions she asked, the measurements she made, and the observatory that continues pursuing the mysteries she first helped identify. If you want to follow this story as the fourth and fifth galaxies in this trail are eventually measured, as Rubin Observatory begins its systematic search for more ultra-diffuse galaxies, and as theorists continue refining the bullet dwarf collision model to account for everything, these extraordinary galaxies are showing us. Subscribe now, because this is one of those areas of astronomy where genuinely major results could emerge at any time.